So let's go into statistical distributions. So we kind of already seen statistical distributions. So this is kind of more statistical distributions. So again, kind of refreshing. It's written as if like we've been a while, so just kind of know that. But basically we're summarizing probability of events. So different distributions just mean different things. So it's a way for us to quickly summarize the data. Remember like I always say, like the data are the data. Like it is essentially like the data are the truth. Like that is like what it is. But a distribution kind of helps us either if we want to say, well, what happened here? It's like, oh, it seems to be like a bell curve. And we can take the data and say, oh, it looks like it's a bell curve. Or we might do the opposite, say, well, our data, we expect it to come out like a bell curve. Let's produce data from a bell curve. We can go both ways that way. Okay, so a uniform distribution is actually pretty simple. Basically, it's just everything is likely. So this is basically some quick math that I think the curriculum actually shows. The standard deviation is equal to basically the 2 points divided by basically the min and the maximum divided by 12, or divided by the square root of 12. And we can see here the average is basically just between those two parts. So if you were to actually graph this out, a uniform distribution, if you imagine like rolling a die, right? And saying, well, you can have a 1, you can have a 2, you can have a 3, 4, and so on. Basically each bar chart, the probability would be the same, right? That would be a uniform distribution. So basically it just means every possibility is likely. Okay, and that's a pretty simple one. That's probably like the simplest distribution we can get to, right? So that is uniform. And so next thing kind of goes into is a normal distribution, which is a bell curve. And oh, this is a great little animation here, is that you can basically see here is that each little ball, have you guys seen this before? Just kind of raise your hand if you've seen something like this before. Yeah, okay. So you can see here quickly, basically, I'll wait for him to come over, is that the balls start off this very, very top and he flips it over. And when he flips it over, the balls fall downward, which I realize, I think this is, no, okay. The balls fall downward from the center, but they can hit a peg, either go left and right. And so sometimes the balls go left and then they go back to right and go left and right. So and most of the time they'll go left and right the equal amount of time, which basically means most of them go down to the middle. But some of them will constantly just hit to the left, 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 to the left. And they actually go way off the side over here. But not many do that. So this actually is showing is that each hitting the peg is a uniform distribution. It's just as likely to go left and right. But when you put these all together, when they're falling down multiple levels, they can basically go off to the left, you know, very unlikely, off to the right, very unlikely. But in the center, they'll go left and right about the same amount of times. And that's where you see this guy right here. Okay. So again, equations like I showed earlier. I'm not going to go through it again, but just know that through this. So next comes up, I'm going to close this because this will distract me. Binomial distribution. So binomial distribution is actually very, very similar to a, what's it called? A normal distribution. But binomial distribution basically says you have the probability of getting the number of successions in a given number of trials. So you can think of this as being like flipping a coin, is like how many times will you have the success of flipping a coin correctly versus like not correctly, sorry. You flip it, let's say, how do I say this? Let's say your success metric is heads for flipping a coin. And you flip the coin, like you're gonna say, I'm gonna flip the coin 10 times. And you flip the coin 10 times and you say, how many heads did I get? Okay, you're like, oh, I got 5 heads, cool, right? And then the next time you try it, you flip it 10 times and you only get 3 heads. And then sometimes you get 7 heads, and one time you get 10 heads out of 10. And that basically, that distribution, if you do that experiment over and over and over again, you are likely to get the actual probability. Your average is in fact basically the probability times the number of times you did it. So if you flip your coin 10 times, right, you'd expect 5, right? 50% of the time it will be on heads. And so you would expect to get 5 heads as your average. And that's where this n times the probability of success is. So if I flip it 10 times, I get the n times the probability of 50, right? Which is give us n times p, which is just 5. Okay. And then our standard deviation comes from here. Basically, it's the same, that n part, but then also the probability of success and the probability of failure. Okay. And you can see here, there's some extra part. I put a little link to Wikipedia. I didn't go into the full detail of this because the curriculum has a lot more detail on the binomial distribution, but I just want to give you some quick notes essentially. All right. So binomial distribution, just know that basically you're just saying how many times did you get a success, which in this case we could measure as heads. We could just as easily say tails, but same idea. Okay. So any questions on binomial distribution? It sounds more complicated than it actually is, but basically it's just saying how many times did you, if you do something over and over again, what would you get? Okay. Cool. So this leads us to negative binomial distribution, which I think is super interesting in this way, is because basically it's you flipping, it's the same idea of you flipping a coin over and over again, but you keep flipping until you hit like a failure point. So let's say, for example, someone plays a game with you. So, okay, you're gonna flip a coin, and every time you flip a coin, I'll like double your money. So like the first time you have it, you have $1. And if you flip the heads, you get $2. And you flip tails, you get $4, and so on, right? But once you hit tails twice, you stop the game. So you might flip heads, cool, flip heads again, cool, flip tails, okay, careful. Flip heads again, oh cool, I'm still going, and flip tails again, you stop the game. That's the negative binomial distribution. Basically it's saying how many times, what's your expected outcome until you hit that failure point. So technically you could maybe go on forever, right? You could maybe flip like 500 times because you're super good at flipping coins and you never get like a tails. But you can obviously kind of like, I saw Giovanni kind of laugh at that because obviously no one's really good at that because it's probability. And that's the whole point, is that by using probability, you can basically determine what the average is. But you can see here, it says R, let me make sure I got this right. Your R is basically your expected like number of times that you're actually going to, like number of times you have to fail. So like you can imagine like, okay, what's gonna, like if you have to have 3, like failures, right? Then basically it's like, okay, well, if you have 3 failures, you're more likely to go further and further into it. Okay, does that make sense to people? You basically just keep flipping that coin until you hit that failure point. And note that failure point, for example, I should like stop flipping at 2 tails. Okay, so what's the probability of getting 9 flips in? And that's what this distribution is going through. It's saying, okay, what's the probability of actually getting like, 9 distributions? And as you increase the number of actual failures that you'll do, your average will change. Okay. Cool. So this kind of leads us into the geometric distribution, which is basically a special case of the negative binomial, which basically just says, once you flip it 1 tail, you're done. Like, and a lot of game shows will have this kind of thing. And so essentially, if you see here, when this R equals 1, come on, do it. Oh, of course, it's taking a second. Okay, there it is. All right, that's the geometric distribution. And so basically, you could technically go on forever and ever and ever and ever and ever. But by having 1 failure, you stop basically doing the experiment. That is what the geometric distribution is, right? So hopefully no questions on that. That's essentially the simpler version of the negative binomial. Okay, cool. So I'll move on to Poisson distribution, which I like to think of it as like the binomial distribution, but it's the continuous version. So this one is kind of, I feel like it's a hard one to, I don't know, say, because flipping a coin, you can see it's games like, okay, I keep flipping the coin, and when I get 2 tails, I'll stop. But this one's much more like usually given like as a certain, what's your stopping point? And your stopping point usually is kind of like, usually given like in an interval of time. So for example, it's like how many people will come into the store within the next 30 minutes? It's like, well, I mean, technically 1 million people could go walking through that door, within the next 30 minutes because of some weird chance, maybe for example, some amazing thing happened in your store out of pure chance and everyone just rushes to it. Very, very unlikely, right? But maybe normally you have about 5 people come in per minute, into the store, which is a pretty popular store. So like you can use that metric and say, well, okay, how many people do I expect to come in over 30 minutes? So again, it's very similar to the binomial distribution, the negative binomial distribution, but we have it on a continuous part. So you can see here, usually instead of using R, we'll use lambda. And that lambda basically is representing that stopping point. And right here is our probability. And so what's kind of cool is that we can get some interesting math that comes out from this Poisson distribution. And again, usually it's used with time, sometimes space, but usually you see this most commonly like when you say it's really famous, for example, that buses coming in, being on time at a bus stop follows a Poisson distribution. So this is kind of where it comes through. Okay. Any questions on that? Okay, cool. And our last part is our exponential distribution, which basically is the continuous portion of the geometric, right? So there is a certain stopping point when it occurs. So one thing, for example, like exponential distributions, particle decay, for example, is basically like, you have how likely is this particle going to last? Like if you know anything about like particle physics, for example, or like, well, anyway, like uranium decay, for example, is that you have a particle, like you don't know the uranium atom when it'll decay, but we'll say like a half-life. And it's like, okay, like when is basically half of them after like, say 500 years or something like that, half of them will be decayed, but you don't know which particular atom will decay within that half time. So some of them could last maybe the next 100,000 years. Maybe the next ones will only last for like the next minute. But the point is basically is that you're trying to figure out when that stopping point occurs. So again, I put the Wikipedia articles here that would be helpful. And again, the curriculum kind of shows a little bit of more equations on here. What you can see here is that the Poisson or the exponential distribution is very similar to the Poisson distribution, since we basically have just one stopping point versus multiple stopping points that could happen. Okay. And you can see here also, you'll see 1 over lambda a lot. And it's because this is usually like this beta usually can be used more frequently. So just know that it depends on who you're talking to on like how they want to phrase the equation. All right, so those are different distributions. I think the biggest new ones are our exponential, our Poisson, negative binomial, and our binomial distributions. Any last questions before I move on to t distributions? Okay, sound good? Thumbs up if it's looking good right now. Thumbs down, you're like, I don't know what's going on. Thumbs sideways, like, maybe not. Okay, some sideways. Okay, let me ask, is it mostly these guys, Poisson distribution, exponential distribution? Well, okay, I'm gonna do it for each one. Does that sound good to you guys? So, all right, so let's start with binomial distribution, like a scale from like 5, meaning I understand this perfectly. 1, like I don't even know what this is. Give me a number. And don't be shy. Like, okay, so I see some hover around 4 and 3. That's okay. Okay, so yeah, just know the big thing is basically saying how many times the number of successes you will actually get within a trial. So again, you basically fix saying I'm only going to do 10 flips of the coin. How many heads will I get? Okay, and so we most commonly will get like 5 heads. Or it's like, okay, well, very unlikely I'll get all 10 heads or something like that. Okay, so that's kind of the binomial. And then how about negative binomial distribution? Let's go from like 1 being like, don't know, to 5, like, oh, I got this in the bag, which I don't expect anyone to have 5, if that helps. Okay, so good. I see a little vary right here, 4, 3, 2. Not Thomas. Tom's not sure. That's okay. But yeah, so negative binomial distribution, it's kind of a similar thing to binomial, but the reason I call it the negative, basically it's like you will stop. Like I think of it like it's the negative side of it. Instead of focusing on how many flips you get to do, you basically focus on you'll keep flipping until you fail. And this is where like we keep flipping it until we get like 2 tails, for example. And note that it's not 2 tails in a row. That's just when we get 2 tails is when we stop. And that's the negative binomial distribution. So you can see basically is that if we have more and more times as R increases, the larger R is, the number of fails that we actually would get is, what's it called? Like as that number increases, for example, if you need like 40 tails in order to fail, well, then that means that you are likely to keep going for a lot longer versus if you only had 1 tail to stop, okay? And kind of going back to geometric distribution, it's just basically when you stop at that 1 failure time. Okay, so it's a special case of this negative binomial. So hopefully that makes sense. So you can kind of see here is that you're more likely to kind of you can technically keep going on forever, but I think this is like a 25% chance of success. So you can see here, if we have R equals 40, well, you'd expect most of the time you would get about 40, or about 10 is your average. Okay. And then a Poisson distribution is basically just the continuous version of this guy right here. Okay. So you can kind of think of it like, but instead of saying like, you know, number of times you fail, it's basically you have like a certain occurrence of like when things will happen. So maybe I misphrased this in a way, but the Poisson distribution, you might say something like, if you have, I don't know, the 10th person to walk through the store, you know, how long will it take for the 10th person to walk through your store? So it can take maybe like a minute for 10 people to walk through the store, or it can take an hour, you know, for 10 people to walk in the store. Maybe it takes 100 years before someone actually walks, the 10th person walks through that store. And that's what a Poisson distribution is. So your failure rate, that lambda rate, basically it's like, when is that point that you would stop? But this part, how far you can go, this K, like that could be like number of minutes. There's a continuous distribution. There's not like a discrete, like, oh, you can walk only at 1 minute, 2 minutes, 3 minutes. Okay, does that kind of clear things up a little bit? Poisson. Yeah, this one's a kind of a tricky one. Okay, and then
a question.
Yeah, go ahead.
So all these distributions are for probabilities, right? Not for actual data points.
So could you clarify a little more, like what you mean by that?
Because you introduced this idea of a failure or a success. So we're not considering, I don't know, a house price, say, but you're considering what's the chance that the house price will be X. Is that what those distributions are? Or maybe can you give another example of failure and success different from a coin flip? That might clear up a little bit better.
Yeah, I'm trying to think of a good one off the top of my head. It wouldn't be so much on the house price. It might be, for example, usually games are a little easier to deal with because they're shorter. If you imagine, I mean, I guess another example of a game would be like the amount of time it would take you to go bust in like, or how many times it would for you to, if you play.
I think what Giovanna was talking about was you would use these distributions with real data points, right? Like a business could say how many times does a customer walk through a door, and you would use this distribution to look at it. That's right, correct? Like you would actually use it for real data. Yeah,
that's right. And is that closer to what you were asking, Giovanna?
Yeah. I'm confused if you're using like actual data points or all these distributions are for probabilities regarding some, you know, hypothesis or example.
Right. Yeah. I think it kind of goes back and forth a little bit. You can either take it as like, if you know what, like you measured things before and you know the probability of an event happening in your store, for example, like if you know like how many people come in per like hour, you can use that metric. Basically that is your probability. And then you can basically define your distribution. Or you can take the distribution and say, well, it looks like this is a Poisson distribution, and then you can pull out the probability from that distribution. So it kind of goes either way in that way. It's kind of like in the same way with a bell curve. It's like, well, if we assume it's a bell curve, we can pull out some information from that. Or if we know that we know what the average is, we know what the standard deviation is from prior measurements, we can then predict and saying, well, okay, what would our future thing look like? So it kind of goes both ways, but yeah, it definitely would have like, it's not something you necessarily have to like say you have a probability. You could also go the opposite where you see a distribution and say, well, we expect this to be a Poisson distribution. So let's measure how many times someone comes through. It's like, well, that's likely the average, and then pull out the probability from that. You can also, which I see more commonly in this way, is you figure out the probability of, you know, a number, like when I say probability, it's like how much you measure is really what probability is. It's like, what do you measure? It's like, well, I measure 5 people come through the store every 10 minutes. And then you can use that as your probability to make a Poisson distribution and predict how likely will we have certain number of people come into the store. Okay. Is that clear up? Cool. Yeah, and thank you, Thomas, for clarifying that a little bit more. All right. And then exponential distribution, just kind of moving on before, or just reiterate, is basically our continuous version of that first stop. Okay, so I'll move on to t-distribution so we have enough time for that. Sound good? All right, cool.